Welcome back, everyone. This is our third video for Chapter 3 on minerals. We finished up talking about physical properties in our previous video. Today we're going to continue on our discussion with minerals. Remember, one of the properties that a mineral must possess is to be a crystalline solid. That is a solid with orderly, regular, repeating atoms at the atomic level. And so the atomic arrangement that results in the basic building blocks of a crystal, we're going to call the unit cells. Looking at sodium chloride, we're going to start with the sodium and the chlorine atoms. Chlorine atoms are in green, the sodium in purple. And we can put them together to create this basic building block of the mineral halite. So it's a collection of building blocks. And here we see crystals of the mineral halite. Unit cells combine to form mineral crystals. So two minerals can be constructed of geometrically similar building blocks and yet have different crystal forms. So let's take a look at a few minerals here with the cubic unit cells. Fluorite, which crystals are cubes, magnetite, whose crystals are octahedrons, and garnets, whose crystals are dodecahedrons. So the top picture here is fluorite, cubed. The mineral form, crystal form here is the octahedron, and this is the mineral magnetite. And then finally, garnets are a dodecahedron crystal form. An interesting observation made by Nicholas Steno in 1669 is known as the law of constancy of interfacial angles. What this says is that regardless of how large or small the crystal is, the angles between equivalent crystal faces of the same mineral would be consistent. So as an example, if we look at the angle between crystal face A and B and this quartz crystal, you could measure that using a goniometer and you would get so many degrees. Now, if you had another quartz crystal and the same crystal faces that you were looking at, but let's say the crystal was huge in size, you would still measure the angle between crystal face A and B to be the same number in degrees. Looking at some structural variations in minerals, let's talk about what a polymorph is. A polymorph is a mineral that has an identical composition with another mineral, but arranges their atoms differently. And a good example would be diamond and graphite. Diamond and graphite are both carbon. However, diamonds arrange their carbon atoms in a completely different fashion than graphite. And in fact, diamond is the form of carbon that is stable deep in the earth, whereas graphite is the form of carbon that is stable near the Earth's surface. So as one polymorph changes into another polymorph, we call that a phase change. So let's look here first at the carbon atoms in the diamond. These are all the carbon atoms. They're strongly bonded with the covalent bond, and it's in an octahedron form. Whereas graphite, which is the lead in your pencil, the atoms of carbon are arranged in sheets. And within these individual sheets, the bonds are very weak. So these bonds here, weak. Within the sheet, they're strong, but between them, very weak. And the weaker the bond, the softer the substance. And we all know that the lead in our pencils are easy to break. Let's talk about some various mineral groups. There are nearly 4,000 minerals that have been named Fortunately, there's only a few dozen that we see consistently in our rocks. And we refer to these as the rock-forming minerals. And these common minerals make up most of the rocks in the Earth's crust and are composed of primarily 8 elements that also are the dominant elements in the Earth's crust. Economic minerals are less abundant, but they are very important for economic reasons. These are minerals used extensively in the manufacture of products. This pie chart shows the 8 most abundant elements in the Earth's continental crust. And we can see that silicon and oxygen are the 2 most abundant. As a result, we have a lot of minerals with silicon and oxygen in them. The other major elements are potassium, magnesium, sodium, calcium, aluminum, and then some miscellaneous. So we can classify our minerals, and what we're primarily interested in are what are called the mineral classes on this slide. And silicates, carbonates, halides, and sulfates are a few examples of mineral classes. Now the class is the big group, and then we can subdivide into smaller mineral groups or species. Okay, I'm over here in the bottom right now. Let's take a look at silicate versus non-silicate minerals. Our silicate minerals dominate the Earth's crust, over 800 known silicate minerals, and accounts for greater than 90% of the Earth's crust. And the basic building blocks of silicate minerals is called the silicon-oxygen tetrahedron. Let's take a look at it, and then we'll come back and talk about the non-silicates. Here is the silicon-oxygen tetrahedron. It is 4 oxygens surrounding a silicon ion. The silicon has a +4 charge, oxygen -2, so the overall charge on the silicon-oxygen tetrahedron is a -4. As a result, positive ions are attracted to the negative silicon-oxygen tetrahedron. Non-silicate minerals aren't as common as the silicates, but they are often economically important. Carbonates, sulfates, and halides are 3 such classes. Here we're looking at a variety of ways the silicon and oxygen tetrahedron can arrange itself. They can be independent tetrahedron, so this is a -4 charge, and so positive ions like iron, magnesium, calcium, sodium will attach, and you give the mineral a name according to what cation has attached to it. We can have silicon-oxygen tetrahedron that are linked in a single chain, double chains, a sheet, and 3-dimensional complex framework. So most silicate minerals form as magma cools, so they're igneous in nature. And the feldspars are the most common silicate group, making up more than 50% of the Earth's crust, followed by quartz, which is the 2nd most abundant mineral in the crust, continental crust that is. And we can take our silicates and subdivide them into light and dark. Light are called non-ferromagnesian and dark ferromagnesian groups. Ferro is iron, magnesium is magnesium. So the light silicates do not possess iron and magnesium, and as a result they are light. What makes the dark silicates dark is the presence of iron and or magnesium. This table is showing the most common silicate minerals. So they give the mineral formula, the name, whether or not cleavage is present, the silicate structure, and then they give an example. So this is worth your time to go through and study, you don't have to know the chemical formulas for these various groups, but just to give you a general idea of the major silicates and what they are, what they look like, what they are constructed of. This concludes our third video on Chapter 3 Minerals. We'll continue on in our fourth video discussing more details about ferro and non-ferromagnesian silicate minerals.